kinetic theory of gases. Now, it's called the kinetic theory because of molecular motion. And anything that moves has kinetic energy. First off, we start with specific heat. Specific heat is the amount of heat required to change the temperature of 1 kilogram of any substance through 1 Kelvin. So 1 kilogram of any substance through 1 Kelvin. But when it comes to gases, since gases can be heated under two conditions, either keeping their pressure constant or their volume constant, gases have two specific heats. One is called the specific heat at constant pressure, the other is the specific heat at constant volume. Another difference is that we would like to define the specific heat not in terms of 1 kilogram, but in terms of its molar mass. And that's why gases have molar specific heat at constant pressure and molar specific heat at constant volume. So let's get there. Molar specific heat, that is the amount of heat required to increase the temperature of 1 mole of a gas through 1 Kelvin. Cp and Cv, because both volume and pressure can be kept constant. All right. So both volume and pressure can be kept constant. That's why we have Cp and Cv. Okay. And Cp is always greater than Cv. That means you need to give more heat than you heat it at constant pressure. So that's why specific heat at constant pressure is always greater than the specific heat at constant volume. All right, let me speed this up. So if volume is constant, then there is no work done because the volume is constant. The gas is not expanding. No work is done, which means all the heat that we're giving is only being used to increase the internal energy. But on the other hand, if you heat it at constant pressure, then the heat is being used in two ways. One part is used to increase the internal energy and the other for work done in expansion. So here is the formula for quantity of heat when the gas is heated under constant volume. NCV dt. N is the number of moles. C sub V is the specific heat at constant volume. dt is the change in temperature. So now let's talk about the energy per degree of freedom per molecule. Now, energy per degree per molecule is 1/2 kBT. Kb is Boltzmann constant. So, to find the energy per degree per mole, you got to multiply this with the number of molecules in 1 mole, which is called the Avogadro number. Excuse me. So that's why we have multiplied it with n sub A. Now, Kb times n sub A is another constant, which is called the universal gas constant R. So, energy per degree per mole is 1/2 RT. Now, for an ideal gas, which is always taken to be monoatomic, there are 3 degrees of freedom. So if the question is about an ideal gas, you should know there are 3 degrees of freedom, and these 3 are the freedom to move along the x, y, and the z axis. And that's why it's called 3 degrees of translational freedom. So, total translational kinetic energy of an ideal gas per mole or per molecule is 3/2 kBt. Now you see where the 3 comes from? We multiplied the 1/2 kBt with 3 because it has 3 degrees of freedom. So here is a question. What is the average translational kinetic energy of an ideal gas at 700 Kelvin? We know the formula that the translational kinetic energy is per molecule, remember it's per molecule, is 3/2 kBt. Now kB is the Boltzmann constant, which is 1.38 times 10 to the negative 23, and the temperature is given as 700 Kelvin. So the answer comes out to be 1.45 times 10 to the negative 20 joules. Remember, that's for one molecule. If you want to find out the translational kinetic energy of 1 mole, we got to multiply it with the Avogadro number. Again, Kb times Na becomes R. So per mole, the answer comes out to be 8730 joules, 8,730 joules. What about if it's a diatomic molecule? Now, in a diatomic molecule, it has 5 degrees of freedom. 3 translational, x, y, z motion, and 2 rotational. Since it has 5 degrees of freedom, the energy per molecule would be 5/2 kBt. If it's a polyatomic molecule, anything more than 2, like carbon dioxide or ammonia, it has then 6 degrees of freedom, 3 translational and 3 rotational. Therefore, the energy per molecule is now 6/2 kBt, which is actually 3 kBt. So remember that. And if you're given the temperature, all you got to do is think about, is it monoatomic, diatomic, or polyatomic, and use the corresponding formula. So let's consider a piston inside a cylinder, and the piston is completely frictionless and it can move in and out. And let's consider that a certain quantity Q of heat enters the system. So there is an ideal gas inside the cylinder, and there is Q quantity of heat entering. What's going to happen is a part of the heat will be used to increase the internal energy. Another part will be used for expansion. That's why you see the dotted line, which is the new position of the piston. So there is a change in volume, and there is work done. So at a constant pressure, remember, this is what happens. The quantity of heat given is used for 2 things. The first part shows the change in internal energy. And the second part is the work required for expansion. And Q is Cp dt, delta E is Cv dt, and work done is PdV. How do you get that? Because work is force times displacement. dx is how much the piston has moved. And so if A is the area of the piston and it has moved through dx, that gives you the change in volume. if you multiply the A with the dx, that gives you dV, which is the change in volume. And P, of course, is the pressure, which is constant. That's how we get work is PdV. Generally, work done is integral V1 to V2 of PdV, where V1 is the initial volume and V2 is the final volume. Okay, so now we have Cp dt is Cv dt plus PdV. Very important, and I'm trying to show you the positions of the pistons now, the original and the new, and the yellow shaded part is the change in volume. But we also know that for 1 mole of an ideal gas, 1 mole, PV is RT. And so using calculus, PdV is equal to RdT. Why? Because pressure is constant, so you take the differential of volume, and on the right side R is constant. So you get PdV is RT. So you can now substitute Cp dt is equal to Cv dt plus, in place of PdV, we are able to put RdT. And now since there is dt in all of the terms, we can just cancel that out, giving us this relation Cp is Cv plus R. That again shows that the specific heat at constant pressure is bigger than the specific heat at constant volume. By how much? By R. So this is called Mayer's relation, M-A-Y-E-R, Mayer's relation, and it's very important. Since Cp is greater than Cv, if you take the ratio between them, you will get what's called gamma, and gamma is always greater than 1. For monoatomic gases, gamma is 1.67. For diatomic gases, gamma is 1.4. And polyatomic gases, gamma is 1.33. You got to remember that. So the ratio of specific heats is always greater than 1, and these are the values. Also remember, if it's an ideal gas, it is considered to be monoatomic, therefore gamma would be 1.67. You need to know that. Now again, at constant volume, we know that Q is the change in internal energy. Why? Because all of the heat that's given to the gas is used only for changing internal energy, because it's not expanding. The piston is fixed. And the change, internal energy is actually 3/2 nRT. That is for n moles of an ideal gas. Where did we get that 3 from? It's a monoatomic gas. Ideal gases are monoatomic. That's why you get the internal energy is 3/2 nRT. N is the number of moles, R is the universal gas constant, and T is the temperature in Kelvin. So if you take delta E, you're going to see that everything else is a constant except temperature. So you get 3/2 nR delta T, which makes it Q is equal to 3/2 nR delta T. But isn't Q also NCV dt? So we have two formulas to calculate the heat given to a monoatomic gas. You can either use 3/2 nR delta T or NCV delta T, depending on what is given. That will be a question on exam 4. We can now put these two equal to each other because the left-hand sides are equal. And that will give us this formula. And you can cancel out the n's, which will give us Cv is 3/2 R. Very important. Specific heat at constant volume for an ideal gas is 3/2 R. What is the specific heat at constant pressure? Well, do remember that Cp is Cv plus R. So if you add R to this, you're going to get 5 by 2 R. And what about if it's a diatomic gas? Then Cv is 5 by 2 R. If it is polyatomic, it's going to be 6 by 2 R, which is 3 R. So those are the values of Cv. Now, moving forward, you have to know the pressure exerted by a gas kept in a container. Here we're talking about an ideal gas. Pressure exerted is 1 over 3 mn v bar squared by v. Now, let me explain the terms. M is the mass of a molecule. Mass of a molecule. N, caps N, is the number of molecules. And in the denominator, we have volume. But what you have in the numerator, v bar squared, is the square of the average velocity. So please remember, one is the velocity in the numerator. In the denominator, you have the volume. Do not cancel them out. Now, m is the mass of a molecule and n is the number of molecules. What do you get if you multiply those two? You will get the total mass, wouldn't you? So m times n is the total mass. So let's write that. 1 over 3 total mass by volume v bar squared. What is mass by volume? It is density. So 1 over 3 rho v bar squared. So from this we can find out a formula for calculating the root mean square velocity, v bar. So you can rearrange that and you will get square root 3p by rho. Remember, one is pressure, the other is density. So if you know the pressure and the density of a gas, we can find out the average velocity. It's called the root mean square velocity. Okay. There's another formula that we could use to find the root mean square velocity, and that is square root 3 RT by m. Now, in this formula, it is very important to note that m is the molecular mass. So if you're talking about oxygen at 27 degrees Celsius, then you can calculate the root mean square velocity. 27 degrees Celsius in Kelvin is what? 300 Kelvin? So you got T as 300. I'm not writing that. And the molecular mass of oxygen is 0.032 kilograms. Yes, it's 32 grams, but 0.032 kilograms. And we can calculate, it comes out to be, I think, 460 something meter per second. That is the root mean square velocity of oxygen molecules. That's really fast. 460 meter per second. Here is one question. A sample of 0.150 kilogram of xenon is in a rigid metal cylinder at a temperature of 20 degrees Celsius. Notice, rigid metal cylinder. That means the volume is constant. If 200 joules of heat is given to the gas, what is the equilibrium temperature? In short, what is its temperature? The molar mass of xenon is 131.3 grams. So you have the mass of xenon and you have the molar mass. See that? You're also given the temperature, but you're asked to find the equilibrium temperature. Why would the temperature change? Because you allow 200 joules of heat to flow into the gas. Let's do this. Now, xenon is monoatomic. Xe, it's monoatomic. That tells us that Q is 3nr delta T by 2. Remember that? Because it's monoatomic. That's where we got the 3 from. Second, we got to find the number of moles. How do you find the number of moles? Total mass divided by molar mass, both in kilograms. Total mass divided by molar mass, and I get the number of moles. Once you get the number of moles, we can go substitute that into the formula, because now we know N, we know R, and we know Q. So you can find the change in temperature. Just make delta T the subject, substitute what's given. Q is 200 joules divided by 3 times the number of moles times the universal gas constant. So that is 14.04 Celsius. So if that is the change in temperature, the increase in temperature, then the final temperature is just the initial plus this change. All in Celsius, so we got 34.04 degree Celsius as the final equilibrium temperature. Okay, so here's the second one. At constant, let's move this forward. At constant volume, we should know that, this is just a review, we should know that all the heat that you give is used to change the internal energy, and that the internal energy for monoatomic gas is 3/2 nRT. So we've done this before, I'm writing it again because it's very important. Q is 3/2 nR delta T for a monoatomic gas. Okay. Or there's another formula, again, which we had done, NCV delta T. So we can put both of them equal to each other. And then if it's diatomic, it's 5/2R. If it's polyatomic, it's 6/2R. The 2 is missing there. Okay. 6/2R. So we know all of that. And then we have the relation between heat, work, and internal energy. This is called the first law of thermodynamics. The first law of thermodynamics. And what's it? The change in internal energy is the difference between the heat entering the system and the work done by the system. Change in internal energy is the difference between Q and W. But remember, Q can be positive or negative. The same thing with the work. If heat enters a system, Q is positive. If heat leaves a system, Q is negative. And what about work? If work is done by a system, it's positive. That is when the gas expands. If work is done on the system, which is when you compress the gas, then work is negative. Right? So I'm explaining the terms. Q is the heat exchange between the system and environment. It could either be positive or negative. I've explained that. And work done by is positive and on is negative. And I've written, when a gas expands, work is done by the gas, and that's why its internal energy decreases. That is, if you don't allow any heat to enter the system and you are allowing a gas to expand, it's going to cool down. Why? Because it's using its internal energy to do work. So in this case, you have a pressure volume diagram, and you have a process from A to B. But the system can go from the initial state A to the final state B along 2 paths. Well, there could be multiple paths, but I've just shown you 2 paths. It could go straight from A to B along path 1, or it can move along path 2. Now, the internal energy is a state function. What does that mean? It means that the internal energy only depends on the initial and final states. That means it's independent of the path taken. Or in other words, very important to know that in this case, the change in internal energy is the same. But work and Q are path functions. See the difference? Q and work, heat and work are path functions. They depend on the path taken, but the change in internal energy depends only on the state, not on the path taken. Okay, let's review. What is an isothermal process? An isothermal process is a process that takes place at constant temperature. So I've given a diagram. Here you can see that there is a gas. You see the molecules of the gas, and heat can either flow in or out of the system. That's why you have the double-headed arrow. And then there are some weights kept on the cylinder. And if you slowly start removing the weights, now then the gas is expanding. The most important word there is slowly. Isothermal processes are extremely slow, which means when the gas is expanding, actually it's supposed to lose its internal energy, but that won't happen because it's expanding slowly. There is ample time for heat from the surroundings to come into the system. And that's why this is an isothermal change. I hope you understand. So when the gas expands, it's doing work, its internal energy was supposed to go down, or its temperature was supposed to go down. But the reason why that does not happen is because the process is slow enough for heat to enter the system. That's why it's an isothermal process. The best example for isothermal processes are phase changes, like melting of ice or boiling of water. Where ice gets converted from solid to liquid, or when water gets converted from liquid to vapor. Remember that in an isothermal process, the system exchanges heat with the surroundings. Remember the double-headed arrow. Heat can flow into the system or heat can flow out of the system. That is an isothermal process. Therefore, if you look at the first law of thermodynamics, then you know the change in internal energy must be zero. Because change in internal energy is NCV delta T, and delta T is zero. Therefore, there is no change in internal energy, no change in temperature, which makes the left-hand side zero. And therefore, let me point that out to you. If the left-hand side here is zero, then Q must be equal to work. So that's important. The equation for an isothermal process is what we get from Boyle's law. Pressure times volume is a constant. That is, so if I give you a problem that says an isothermal process, you can use this equation. Pressure times volume is a constant, or P1 V1 is equal to P2 V2. How do we find the work done? The work done is integral V1 to V2 PdV. But in an isothermal process, we can use this PVs and RT. And all of the terms on the right-hand side are constants, so it's equal to K. So I can substitute for P as nRT by volume. You see that? I'm not using the K part now. I'm just using P is nRT by V. Substitute that back here. All of them are constants. It's taken out of the integral, leaving us with 1 over V dV. And integral 1 over x dx is natural log of x, isn't it? So when you do the integration and substitute the limits, you're going to get natural log V2 by V1. That's the formula for work done in an isothermal process. You should be able to use that to calculate the work. So if I say a gas expands to double its original volume, then you know V2 by V1 is 2, right? Because it expanded to twice its original volume. And then if I give you the number of moles and the temperature at which it happens, you sure should be able to put it into this formula and calculate the work done in joules. So let's see. It takes 500 joules of work to compress quasi-statically. What does that word even mean? Quasi-statically means false static, or in other words, it's extremely slow. That means it's an isothermal process. It takes 500 joules of work to compress quasi-statically 0.5 moles of an ideal gas to 1/5 of its original volume. So the gas is being compressed to 1/5 of its original volume. Calculate the temperature of the gas, assuming that it remains constant during the compression. Okay, so what is the formula for work in an isothermal process? It's nRT, natural log V2 by V1. Number of moles is given, 0.5. R is the universal gas constant, which is 8.314. We do not know the temperature, but we know that it's 1 by 5. V2 by V1 is 1 by 5. Now, why did I put negative 500 here? Very important to know. When work is done on a system, it's negative. Here, a gas is being compressed. You're doing work on the gas. That's why it's negative 500. And then on the right-hand side, when you plug in all these, you're going to get negative 6.69 times T, which we do not know. So it's easy to rearrange that and find the temperature. Negative by negative is positive, and you get the temperature to be 74 Kelvin. Take note of this. Very important. Okay, what do we have here? Again, you see a system, but this time the system is completely insulated from its surroundings. So if you have a gas in here, that gas cannot exchange heat with its surroundings because it's in an insulated system. No heat exchange is possible. Now, this is the complete opposite of an isothermal process, and this is called an adiabatic process. No heat exchange is possible. It's called an adiabatic process. It's usually a very fast process. And I've given the example of thunder and lightning. Thunder is adiabatic expansion of the atmospheric air so rapidly that you hear that loud sound. So an adiabatic expansion always leads to a decrease in temperature as the internal energy decreases. So the gas is expanding so fast that it has to use its own internal energy to expand, so its internal energy drops, or in other words, its temperature drops. Okay, so if you apply the first law of thermodynamics to this condition, you're going to get Q is 0, because Q is what? The heat entering or leaving, which is 0 in this case, and then you end up with change in internal energy is negative of the work done. Remember, work is positive expansion, therefore internal energy is negative in this case. But if a gas is rapidly compressed, then the change in internal energy will be positive. I hope you understand that. Now, for an adiabatic process, we can derive the formula using these steps, but I'm not going into details. You can follow it along if you want to, because what I've done is the change in internal energy is CV dt, and then the change in internal energy is dq minus the work from the first law of thermodynamics, but dq is 0 for an adiabatic process, and CV dt is negative pdv because of that, and then I get the value of dt. Simple math, take your time to look at it. I'm trying to derive the equations for an adiabatic process. For 1 mole, this is the ideal gas, PV's ideal gas equation, I mean. And now if you differentiate on both sides, you have to use the product formula. So PdV plus VdP is R dt, On the right side, R is a constant. So now again from here, we can make dt the subject. If you make dt the subject, you're going to get pdv plus vdp whole divided by r. Now we have two equations, and the left-hand side is the same for both. It's dt. So what we'll do is we'll put the right-hand sides equal to each other, and I've written that again. So you see, let's take it over from here. I put the right-hand sides equal to each other, did some algebra there, cross multiplying, as you can see. I also substituted for r as Cp minus Cv. That's why instead of r pdv, it's r times, it's actually Cp minus Cv times negative pdv. And then on the right side, it's just cross multiplication of this. And then do the algebra, you see that these two terms cancel out. Whatever remains is this, divide both of those terms, all three terms actually, also on the right side with this. If you do that, you are going to get gamma here, Cp by Cv, you're going to get integral, you're going to get dp by p, and then I'm integrating this expression, and I get gamma natural log volume plus natural log pressure 0, which is, in a sense, PV raised to gamma is a constant. So do not worry about how I get the formula, but this equation is very important. And this can only be applied to an adiabatic process. Pressure times volume raised to gamma is a constant. There are actually two other versions which you can easily get by substitution of the ideal gas equation. And here I've listed all three equations that can be applied for an adiabatic process. So make note of this, and you should be able to use this to find, the temperature, the volume, or the pressure, whatever be the case. All right, so let's find out the work done during an adiabatic process. Now, to find the formula for work done, we always use the basic integral V1 to V2 pdv. But because it's an adiabatic process, we have to use PV raised to gamma is constant and substitute for P. So P is K by V raised to gamma, substitute that back into this. So, and then integrate, K is a constant, it's taken out. I know I'm going fast, but you should be able to follow along. And what's the integral of that? That is V raised to negative gamma plus 1 by 1 minus gamma. And then when you substitute the limits for the volume, you will get V2 1 minus gamma minus V1 raised to 1 minus gamma. And then I'm taking the K inside, I'm multiplying both the terms with K. You see this K with this and this K with this. But the trick is K can be given either the value P1 V1 raised to gamma or P2 V2 raised to gamma, because it's a constant. So for the first K, I'm going to give it the value P2 V2 raised to gamma. For the second K with this, I'm going to give it the value P1 V1 raised to gamma. You'll see that, and you will understand why I'm doing that. So when you do that, you see that two terms will cancel out. I'm just explaining why I gave that, because like I told you, K could either be P1 V1 raised to gamma or P2 V2 raised to gamma. Okay, let's continue. So now we have work is 1 by 1 minus gamma, and inside you see that V2 raised to negative gamma will cancel out with this, and so likewise here V1 raised to negative gamma cancelling out with this. So you're left with an excellent formula, which is 1 over 1 minus gamma P2 V2 minus P1 V1, which is used to find the work done during an adiabatic expansion. We can get other formats of this by knowing that P2B2 is nRT2, ideal gas equation, and P1B1 is nRT1. And you can pull out the nR, and then you will have it in this way. We can also do another thing if required. We can substitute for R and gamma. Okay, but I've not done that. So we could have done that, R and gamma. Gamma is Cp by Cv, R is Cp minus Cv. We could do that. But you need not. These are two very important formulas that you need to know. Here's the first one. Here is the second one. You need to know both of these formulas to calculate the work done during an adiabatic process. Okay, let me get that out. Let's work out some questions. I think 3 or 4 problems, and that'll be the end of this video. In a quasi-static isobaric expansion, 500 joules of work are done by the gas. If the gas pressure is 0.808 atmospheres, what is the fractional increase in the volume of the gas, assuming it was originally at 20.0 liters? So what do we have? It's quasi-static isobaric, very slow process that takes place at constant pressure. The work done is 500 joules, and that's the work done by the gas. Pressure given in atmospheres, and then you've got to find the fractional increase in the volume, assuming that the original was 20.0 liters. Okay. So here, because it's an isobaric process, the formula for work is pressure times change in volume. Where did I get that from? Because work is generally P dV. And what is dV? Change in volume. Now, this can only be done because the question says it's an isobaric process. That means the pressure is constant. Now, the pressure is given in atmospheres, and I'm changing it into pascals, and then change in volume. We do not know the final volume, but we do know the initial volume. And I did change that into meter cube. 20 divided by 1,000, because 1,000 liters make a meter cube. So do the math now, and you could calculate the final volume. I'm not going to explain that. You can do that, and you get the final volume. Once you get the final volume, it's easy to find the fractional increase in volume. How do you do that? You find the change in volume divided by the original volume. Okay? So this is the ratio. Now, I put that back in liters because, as long as both are in liters, the fraction is the same. So it's 1.3 times. In other words, the final volume actually increased to 1.3 times the initial volume. But really, if you want to do the fractional increase, you got to go 1.3 divided by 1 times 100, which will give you 30%, which I've not done. Here is the second question. Oh, it looks like it's the same one because it's again a quasi-static isobaric expansion. 500 joules of work is done by the gas. Gas pressure is the same. The original volume is the same. But look at the difference. If the internal energy of the gas increased by 80 joules in the expansion, how much heat does the gas absorb? So the gas is expanding, and it's supposed to lose internal energy, but it says the internal energy increased, which means heat was flowing into the system from the surrounding. And that's what you have to find. So, change in internal energy is Q minus the work. That's the first law of thermodynamics. Change in internal energy is given as 80 joules. You're asked to find Q. The work done by the gas is positive, so that's why we have negative times positive. So you got Q is 580 joules. Okay, nothing can be more easier than that. Here's the third one. An ideal monoatomic gas at a pressure of, I'm not reading those numbers to save time, the pressure given, the temperature given, It's a quasi-static isobaric expansion from an initial volume to a final volume. What's the work done? What's the temperature of the gas after the expansion? How many moles of gas are there? What is the change in internal energy? How much heat is added? Oh, there are 5 parts to this question. Let's do it. It's an ideal monoatomic gas. Because it's isobaric, the formula for work is P times V2 minus V1. Pressure is given in pascals. Volume in centimeter cube, so I have to change it into meter cube. So see what I'm doing. Divide by 10 to the power 6. Because 1 meter cube is 10 to the power 6 centimeter cube. All right? That explains it. 100 times 100 times 100. So that is 10 to the power 2 cube, which is 10 to the 6. You got it? I hope so. And do the math. You get 400 joules. So that's the work done by the gas. All right. Second part, what is the temperature of the gas after the expansion? P1V1 is nRT1 and P2V2 is nRT2. So when you take the right hand sides, NR is the same, so we can put it in this format. And then we use the pressure, initial volume, divided by the initial temperature, which is given as 300, is equal to the final pressure given. And we have the final volume divided by, we do not know the final temperature, which we can easily find. All right, and we get it as 600 Kelvin. Isn't that an easy question? It is. Now, how many moles of gas are there? So, the C part. Well, we can use the ideal gas equation and calculate N. Yep, N is P1V1 by RT1. So, simple substitution of the initial pressure, initial volume divided by R is 8.314, and the initial temperature is 300 Kelvin. Just do that and you get, oh, why did I have 10 to the 6 there? Yeah, because I had to change centimeter cube into meter cube. Calculate that and you will get the answer. It's 0.16 moles is what I got. Excuse me. And then the D part. What do we have to find? What is the change in internal energy? Go back to the first law of thermodynamics. And also remember that change in internal energy is 3 by 2 nR delta T for a monoatomic gas. Because of 3 degrees, that's why we have that number 3. We know the number of moles, we know the ideal gas, we know the universal gas constant, and delta T is the change in temperature. Is it 300? Yes, it is. Because the initial was 300, the final was 600, the change is 300. And do that and you will get the answer as 599 joules. Now on to the last part. How much heat is added to the gas? This is where you go to the first law of thermodynamics. We got the change in internal energy. And we know the work done, so you can just make Q the subject and do the little algebra. Okay, work done was what? 400. It's on the previous slide, so the heat that was flowing into the gas was 999 joules. All right, on to the last question. An ideal gas expands isothermally along AB and does 700 joules of work. How much heat does the gas exchange along AB? Then the gas expands adiabatically along BC, does 400 joules of work, And when the gas returns to A along CA, it exhausts 100 joules of heat to its surroundings. How much work is done on the gas along this path? So 3 parts. Let's do it. So it's an isothermal expansion first. It's an ideal gas. Okay. Here's the first law of thermodynamics. And then from there, we know because it's an ideal gas, it's monoatomic, therefore its delta in the change in internal energy, is 3/2 nR delta T. Delta T is 0 because it says isothermal expansion. That means there's no change in internal energy. Oh, so easy. That means all of the heat, is flowing is the work. Q is equal to work. Done. Now the B part. Now it's an adiabatic expansion, and it says it does 400 joules of work. So because it's adiabatic, remember that change in internal energy is there, but Q is 0. Q is 0. And that's why we get the change in internal energy is negative of the work. Just from here. If you put Q is equal to 0. So we get negative 400 joules. That is the change in internal energy. And therefore, Q is negative 100 joules. From the question, when the gas returns to A along CA, see that? It says it exhausts 100 joules of heat to its surroundings. Means it gives out. So that's why I put it as negative 100 joules. Now that is for the path CA. So the total change in internal energy is, it lost 400, it lost 100, so the total change is, of course, loss of 500 joules. Negative 500 joules. And once you get that, we can go back to the first law of thermodynamics. And because it's an adiabatic process, delta Q or Q is 0, we get back to this. Work is negative of that. That means you got 500 joules of work. So it's just logic and applying the first law of thermodynamics, you see, to these problems. And that's how you get those. Oh, there's one more. And this must be an important question, correct? An ideal diatomic gas is slowly compressed adiabatically. Oh, although it's slow, it's adiabatic. To 1/3 of its original volume, what's its final temperature? We have to use one of the adiabatic equations. And because we're talking about volume and temperature, it's going to be the one that involves temperature and volume. But gamma is 1.4. How do I know that? Because it's a diatomic gas. And V2/V1 is 1/3. It says that in the question. T1 is 80 Kelvin. What's T2 is the question. All right. Here is one of the adiabatic equations. Take note of this. Substitute the values. T1 is 80. We can make T2 the subject and substitute the values into that. And so we get, you can just take V1 over V2 whole raised to gamma minus 1. That's 80. V1 over V2 is 3. Remember, it's V2 over V1, which is 1/3. That's why I put this as 3. It's the reciprocal of that. And then when you complete the calculations, you will get 124 Kelvin. Is the final temperature supposed to be higher? Oh yes, because you're compressing the gas. And remember, in an adiabatic process, the temperature always changes. So that's what I have for you. Now there's another question. All right, let's see. Okay, so that is the last one. So here is the last one. In this case, the gas expands adiabatically from an initial volume to a final volume. Initial pressure and temperatures are given. What are the final pressure and temperature? See, I'm trying to show you how to use the other adiabatic equations. So remember that there are 3 adiabatic equations. We're using this one to calculate A. I don't think I have to read everything out because you can see what's given and what's not. So we're trying to find the final pressure. And the final pressure is just the initial pressure times the ratio of that volume. Volumes are both given, raised to gamma. And gamma is 1.67. Why? Because it's a monoatomic gas. 5 by 3 is 1.67. Okay? So we get A. And then B, oh no, we also have to find the temperatures. So you get the temperature using the other adiabatic equation. Just pause the video if you think I'm moving too fast and then see what I've done. It's just algebra. But make sure you study this, okay? So when you do that, you get the final temperature. Okay, and you get 259 Kelvin, and then there is a C pod. No, there is a B pod where in an isothermal process, so it's now saying it's isothermal. The ideal gas expands from an initial volume to the final volume. It's actually the same numbers. If the initial pressure and temperature given, what are the final pressure and temperature? Oh, this is so easy. Because it's isothermal, the temperature will be the same. We got the answer. Now we got to find the pressure using the isothermal equation. And what is that? That is pressure times volume is a constant. So I'm trying to show you the difference. You know, if it's adiabatic, use the adiabatic equations. If it's isothermal, use the isothermal equation. It's as simple as that. So that's the pressure and the volume initially, and set it equal to the final pressure which we're trying to find, and that's the final volume. So when you do the calculation, you're going to get the final pressure as 4.0 times 10 to the 5 pascals. And now the temperature, I already told you. I think I told you that temperature does not change because it's an isothermal process. That's all I have for you. I had to make this quick video right before the final exam for the sake of my students. But wherever you are in the world, I hope it's been useful for you. Why don't you take 1 minute to post a comment, to tell me if it's been useful, or if you want to criticize constructively, please go ahead and do that. Thank you for watching this video. Have a good one.